Okay, let me continue. It's now 10 minutes to conclude this lecture. And next week, we will see together the implementations. Of course, next week I will tell you also some specific aspects. Yeah, okay, this is running. Now, again, on the problem, how many measurements and how long is the window? And a practical way to recognize this aspect here is again to look how many parameters I have to estimate. Look here, for instance. You can see that I have two parameters to be estimated, parameter R and parameter L, parameter R and parameter L. And during the discretization, we can see that the structure allows me to formulate or to write in a possible model which consists of two parameters, because I need in any case two parameters, but also we can see in accordance with the dynamics that I need, for instance, just one past output, the present output, of course, and just a past input. Just comparing. Of course, there is method in order to say this directly observing the analyzing the dynamics from here. I don't want to insist on this because here I didn't tell you much about the dynamics, about the differential equations. But of course, we can see a little bit what I intend, because we can see that the current, which is our output, is a function. If you do the integral here, what is the current? Is the integral of the right part. This means, if you remember what the integral is, the integral is an inertia. Just I give you some practical inputs without theoretical aspects. Think about the current is the integral of the right part. This means what I have in the right part, if you think about the inertia of the integral, is something, let me say, delayed with respect to the current, or the current on the right part, on the left part. The current I of t equals the integral what I have on the right part. If you remember in high school, the meaning of the integral, or in my courses, automation or dynamical systems, probably, the integral realizes, or the effect of the integral is in a phase delay. Do you remember this? It's in a phase delay. I will insist on this a little bit later. Do you remember this? The integral is in a phase delay. Electrotechnic, we have seen many times. In discrete form, the phase delayed is delayed in time. This means at least if you have an integral, and Ts delayed in accordance with the sample time which I use. Now, roughly speaking, really intuitive. In fact, we can see, at least I would like to say, using this forward Euler approximation, because if you use backward approximation, is something different. About that we can discuss a little bit more in depth. About this. This of course depends also on the approximation which I use. Let me remain on intuitive, an easy example with the forward Euler approximation. In fact, what I told you, at least with forward Euler, we can see here the current on the left part equals something which is in the right part but delayed with forward Euler. Now, the situation is complex, if I say, but depends of the approximation. Yes, depends of the approximation too. I don't want, at least today, I don't want to tell you about that because it's already too much in the sense. This could be a practical criterion to understand how many elements have to consider in the past, 2 elements in this case, and which one. I mean, I have to measure 2 outputs. We can see here y of k and y of k minus 1 and the window and 1 input. Next week I will implement, and then we will come back. I don't have time to tell you about the backward Euler, but some other approximations. But sometimes we need different approximation for different reasons. I don't know if you heard about stiff system, probably a little bit I told you about in dynamical system. We will eventually consider this aspect here in projects. We use backward, for instance, in Rolls-Royce. We generate also interesting results because we have a stiff system, which we have two really different dynamics. And then we can understand very well that if the goal is to estimate L and R, this is the goal. Of course, if I am able to estimate theta 1 and theta 2, I have 2 equations and 2 variable. Let me think what what I can say. Nevertheless, please pay attention here. These two equations, if you look at the equation, they are in general non-linear because theta 1 divided theta 2. I will tell you at the end of next week, at the end of the, Laura, 5 minutes, at the end, because it's nice if you can stay, because I will show you the implementation and some problems connected with the implementation, and I will advance a little bit. I will give you some hints related to some variation of this. Everything, nevertheless, is related to the observability concept. Is the system observable? Is the system not observable? This aspect here, I typically consider the observability in another course, but I will sketch a little bit also here the problem next week. Concluding this, in order to analyze theoretically a little bit this system here. If you look at this equation here, which is the equivalent at the same form in the sense that the derivative of the current reflected energy equals something on the right part. We can see that we have the derivative at this level here and the derivative of this level here. This means, in accordance with the dynamics of the system here, just roughly speaking, we have something we change on the left part equals something we change on the right part. This means now the time, let me say, related to the left part is not totally delayed because the change here is exactly equals the change, the part of the change of the right part. We can see this, the change of this element here equals the change of this element here plus or minus something like that. This means if you do the derivative, the discretization of this, we are waiting that something on the right part change at the same time on the left. If you do the calculation, again, using forward Euler, this is nevertheless is an hypothesis. About backward, we can do a project together eventually. This could be nice because can be used backward, or Runge-Kutta you heard about, Runge-Kutta or Oyen, this is, other methods to realize the discretization. I will tell you about the discretizations in the second part of the course when we attack the problem of control. I will go in depth on these methods. Look, we can see that here we have something we change at the same time of the output. This means we have an asynchronismus, if you want, between output and input. And then we have to take into consideration this. We can see here. In this case, it's easy because we can see that we have the same parameter which multiply the input at time k and at the time k minus 1. But it could be also, it could happen that I need you input k minus 2. Like here, it could be that I need the current I of k minus 2. This depends, please pay attention, depends, in one word, of the order of the differential equation if you consider here in a system with the second order, second derivative and so on. Or if you consider a system, I don't know if you remember, in linear case, we'd have zero in the numerator, or in general, zero dynamics. It's a concept extremely complex. I introduced very shortly in the automation, but depends what we have here in the transfer function, or in general, if you don't consider transfer function, zero dynamics. How the input plays in a role in the dynamics. I come to you with the last question. Here we can understand that we have a zero. For S equals 0, I don't know, for engineer is clear what I intend, but in general, how the input works on the dynamics, we can see here. If you look at this from Kirchhoff law, I don't know if you remember that UC is 1 divided C integral of this. We can see in a totally different dynamic. This means that here the voltage here is delayed. We can see here with respect to the current. We can see here. This is the voltage, which is delayed with respect to the current. This means if I want to calculate the derivative of the current, we can understand very well that we have a derivative here. I don't know how change the current here. Change immediately. If you have, for instance, in a shutter, in a switch, when I close, we have a current which is not constant, is in a step. This means, in general, just roughly speaking, depends really of the dynamics. How many derivative I have, second derivative, second system of the second order, but also how the inputs influences the output. If you close here with the battery, we have the current, which is our output. We change, not continuous. No? We have a step. The current. We will go in depth next week, but we can see here that nevertheless, I need just 2 parameters because we have to estimate C and R, the parameter to estimate in CR as before, but I need 1 measure more because I need also UK, U input K. It is not enough as before U input at K minus 1. I need U input of K, but it's possible because as before, the system is the system of the which consists of first order, just 1 differential equation. The window consists of 2 elements, and that depends what I have to consider. 2 times input, 2 times the output at time K and time K minus 1. In this case, we need also not only the U input at time K minus 1, but also the input at time K. We can see also how we obtain a system, an algebraic system, just comparing this expression here with this one. And because the parameters is 2, and I can calculate the C and R. I can calculate C and R. When I have theta 1 and theta 2 from the measurements. Okay, thank you. Yeah, thank you. Next week we have the possibility to do all the normal lecture, and I will implement everything. And in particular, I will extend with some possible idea for projects, no? Including disturbances, including also non-linear, because at this moment we are considering linear systems, but can be also used for non-linear. What is the idea? Theta 1 and theta 2 will change over time, We will see here in the simulation, theta 1 and theta 2 will change over time just in the transient. If the system is non-linear, we'll continue to change over time. Thank you for attending the class. Excuse me for the problem of today. Next week, we will do a little bit better. Let me close here if you have a question.
Wenn wir diese Verschiebung haben, müssen wir die ausgleichen. Das ist mir jetzt nicht ganz klar. Sorry, ich muss auch jetzt zum Modul, weil